So for the second question, we have to come up with an expression for the for the flow over a flat plate, and we have to consider the boundary layer regime. So first we will start by this is a flat plate, and here is the free stream velocity u infinity, and this is the boundary layer growing. We consider a point and the growth of the boundary layer in it, and we will start by writing the 2D Navier-Stokes equation. So for the continuity equation, we have del u by del x plus del v by del y is equal to 0, and for the x momentum equation, we will write del u by del t plus u del u by del x plus phi del u by del y is minus 1 upon rho del p by del x plus nu del 2 u by del y square. So for now for the boundary conditions, we have at y equal to 0, we have u is equal to 0, and at y is equal to infinity, we will have u is equal to u infinity, and not u infinity, it will be 10 to u infinity, and del u by del y will be 0. So similarly, del 2 u by del y square would be 0. So if we analyze the equation around the y is equal to infinity, the x momentum equation will say us that so if we consider the flow to be steady, so this would be 0, we can arrive that del p by del x equal to 0. The one thing is this, and we can have the equation as u del u by del x plus v with v del u by del y is equal to nu del 2 u by del y square. So this is the momentum equation we have. This is the first and this is the second. So if we seek a similarity solution, so we can write neta as y by delta. So here with the growth, like where delta represent the growth in the boundary layer as we move in the horizontal direction. So the growth in the vertical direction is represented by delta, and we assume it as a function of x. So if we want to seek a similarity solution, so we can have neta would be a function of y by delta, neta as an expression y by delta, and we can write u by u infinity some function of h by neta. So we have u is u infinity h of neta. Okay, so to satisfy the first equation, the continuity equation, we assume a stream function psi which satisfy the first equation. So we know for the stream function we have u as del psi by del y and v as minus of del psi by del x. So expressing u as del psi by del y means u is del psi by del y can be written as u infinity times h of neta. So we have psi is equal to integration 0 to y u infinity h dy plus some function of x, and if we replace y by neta for the integration, so we have phi is equal, if we change the limits, it would be what would come, or delta would come, yes, delta h d neta plus some k of x. Okay, so delta is only a function of x, and u infinity is a constant, so we have psi is u infinity delta integration 0 to neta h d neta plus kx. If we assume this to be a function of neta, say f of neta, so if we can write u infinity delta f of neta plus some kx. Okay, so now the stream function would be having a constant value at y at the wall or at the flat plate at y equal to 0. Some phi would be equal to some constant, so let's say it's 0. So this would give us that k of x would be 0, and then we can write psi simply as u infinity delta and f, and from here we also would have that f of 0 has to be 0. Okay, so now expressing now we have this psi expression from which we can write the expression, we can write the u and we can write the v, and similarly we can obtain the expression of del u by del x, del u by del y, del 2u by del y square, so we can replace it back in the momentum equation. So we have u as simply del psi by del y, which would give us u infinity delta f dash del neta by del y, and del neta by del y is simply 1 upon delta, so it would give us u infinity f dash. So we have u as u infinity f dash. Okay, and if we analyze del u by del y, it would simply be u infinity by delta f double dash, and del 2u by del y square would be u infinity delta square f triple dash. Okay, so for v we would have minus of del psi by del x, which would be minus u infinity delta times f dash del neta by del x plus f del of delta by del x, and del neta by del x would give us del neta by del x would give us minus y by delta square del of neta is y by delta. Okay, minus y by delta square del delta by del x, and y by delta we can replace it minus neta by delta del delta by del x. So if we replace it back, we would simply have okay, let me do it on the next page. We would simply have v as minus of del psi by del x as u infinity del x neta f dash minus f. So we have obtained v, we have obtained u. Okay, we have to obtain del u by del x also. So for del u by del x we have simply u is u infinity f dash, so it would be u infinity f double dash minus neta by delta del delta by del x. So we have obtained all the expression. Now if we replace it back into the momentum equation, in the x momentum equation, we would have u which is u infinity f dash, and del u by del x, again this is u infinity whole square f double dash minus neta by delta del delta by del x plus v del u by del y. V del u by del y would involve u infinity del x neta f dash minus f. V del u by del y is simply u infinity whole square by delta f dash f double dash, which will give us nu del 2u by del y square. Del 2u by del y square is simply u infinity delta square f triple dash. Okay, so if we solve this equation, there are much terms which would cancel out. U infinity would be common, delta would be common, so we arrive the expression of f double dash plus u infinity delta by nu del delta by del x f double dash equal to 0. Okay, so this is the expression that we have achieved, and to achieve the expression asked in the question, we would have to take this constant to be 1, so that this expression becomes an ordinary differential equation. So if we take this one, we have the final expression as f double dash equal to 0. So the first part of the question we have solved, where we have arrived to this expression, and now this expression could be solved to have the solution of delta with respect to not 0, it would have to be 1. We have made the constant 1, and can be solved further to obtain the expression of v infinity, tau, cf and cd, which would be plotting in MATLAB. One more thing is left. We have to arrive at the boundary conditions in terms of f. So we have mentioned the boundary conditions in terms of u, but the one boundary conditions that we have arrived is f of 0 is 0, which is a Lilly, but as y tends to infinity, we would have neta tends to infinity and u tends to u infinity, and u tends to u infinity will give us u infinity is equal to u infinity f dash neta tends to infinity. It would give us f dash neta tends to infinity is equal to 1, and the other boundary layer conditions for which what we can do is del u by del y would be 0. So del u by del y would be 0. Would not give us a boundary condition. What we can do is as y tends to 0, we have okay, as y tends to 0, we have u equal to 0, which will give us f dash neta and 0. So these are the f of 0 equal to 0, f dash 0 equal to 0, and f dash and neta tends to infinity equal to 1 are the three boundary conditions which would be using.